Next assignment, you are building upon your understanding of binary and how it's used on a computer. So it turns out that everything on a computer is represented in binary, zeros and ones. And the reason for this is because computers use these little tiny switches on their circuit boards called transistors. And they are switches basically, which means that they have two states, on and off. So there's either current going through them, which is on, or there's no current going through them, which is off. And we can think of on as 1 and off as 0. And so basically, what a computer does is with these zeros and ones, there are different encodings. And what encodings are is you can think of it kind of as a translator. So, in one context, binary might convert to maybe just regular base 10 numbers for us, depending on its encoding. Uh, However, in a different context, if there's a different mechanism for encoding, you could translate binary numbers, zeros and ones, to an image on your screen, or even text messages on your phone or on a website. So even like these words that you see on the screen, technically they're being represented by just zeros and ones on your computer, and it's using a particular type of encoding and decoding in order to translate those zeros and ones into the text. So what we're going to see is what is one of these encodings. So one way to encode text on a computer is with the Ascii standard. And so ASCII is the American Standard Code for Information Interchange. Now, technically, we currently use, most people currently use UTF-8, but the encoding for these ASCII pretty much remains the same in UTF-8. But I think it's a really good place to start. So if we look at this chart, you can see how each of these 8-bit numbers, if you count these, there's 8 bits in here. Each of these 8-bit numbers maps to a different symbol or character on your keyboard. And not only are the letters of the alphabet here, but you can see that you see capitalized and lowercase letters, and their um, their bit, their sequence of bits is actually different. So capitalization does matter here. You can also see that space is a character also. So this is not the word space, but the actual, like if you hit the space bar, that is a symbol on the computer. You can see underscore, tilde, and all sorts of different symbols. Now, of course, this isn't the limit of all the symbols that a computer can encode, but this is just a subset as part of ASCII. So what we're going to do for this assignment is you're going to practice encoding and decoding text using binary. So if I open up this activity guide, in your copy, you will have, on the first page, you will have an example. So this kind of just walks you through what I just talked about, how everything on a computer is represented in binary. And then down here, you'll see an example. So this sentence here, CS is rad, has 1, 2, and then remember spaces are characters too, 3, 4, 5, 6, 7, 8, 9, and then the punctuation, 10. So 10 different characters. And each of these 10 characters are represented by an 8-bit binary number. Brief reminder that you should understand that 8 bits is also called 1 byte. So each of these characters is represented by 1 byte of binary. Remember that also spaces and punctuation are included in this set of symbols. When you're doing this assignment, you'll be using the ASCII table. So let me actually open that up here. So if I take a look at this table, and I try to look up the capital letter C, for instance, I can find that right here. Okay, so I know that in the computer, this capital letter C is being represented by this binary sequence of 8 bits. And then for your understanding, we've also included the base 10 number. So this binary number is actually the same thing as 67 in base 10. And so what we want to do is we want to go ahead and translate sequences of characters, like the sentence, into binary, and the reverse. Given a sequence of binary, translate it to a message that is in text. So what this example shows you is how I took this sentence and I used this table to find out the binary values. So I looked at the capital C and then I found the capital S and found that binary. I found also the space, since there's a space in between CS and is. I found that as well, plugged that in. And then at the end, after I found all the values, I put all the binary bits together because that is what the complete sentence would be represented as in a stream of binary digits, bits. And in reality, these spaces wouldn't matter here. I just put that for readability. Okay, so after this example, I gave you a sentence to decode. So here is a sentence that's represented entirely in binary. And what you want to do is you want to use the lookup table to find the letter. But the trick is that you want to translate these binary digits to base 10 first so that you can find them more easily in this table here. So that's where the flippy-do comes in handy. So you can see that this first value here is 0, 1, 0, 1, oh, 0, 1, 0, 1, 0, 1, 1, 1. So that's going to wind up being 64 plus 16, and then these 4 plus 2 is 6, and then 7. So if we add all those together, we are going to get 87. Okay, and then 87, if we look that up, so first I'll put the 87 here, and then we'll look that up in our table. 87 is going to be a capital W, so we'll put that right in there. And remember, capitalization does matter, so make sure it's capital W. And then the next value is going to be 0, 1, 1, and then 0, 1, oops, 0, 1, 1, 0, 1, 0, 0, 0. So now if we add those up, it's going to be 64 plus 2 plus 8, and that's going to be 104. So I'll put 104 there. Oops, 104. And then we'll look back at the ASCII table. 104 is going to be a lowercase h. Okay. And then for the next one, we have 0, 1, 1, 0, 0, 0, 0, 1. And that is going to be 64 plus 32, and 1 is 33. So that's going to be 97. And that's going to be 97 is going to be over here. It's the lowercase a. And then our next value is going to be 0, 1, 1, 1, 0, 1, 0, 0. So that's 64 plus 32 plus 16 and 4 is 20. That is 116. 116 is going to be lowercase t. And then our next value is going to be 0, 0, 1, 0, 0, 1, 1, 1. And that's going to be 32 plus, this is altogether 7. So that's going to be 39. So if we look at what that is, 39 is apostrophe. So that's our apostrophe. And then for the next value, we are going to have 0, 1, 1, 1, 0, 0, 1, 1. And that's going to be 64 plus 32 plus 16 and then plus 3. All right, so that's going to be 115. And 115 is a lowercase s. All right, next one is going to be 0, 0, 1 and then all zeros. So that's going to be 32. Just plain old 32. And that I kind of remember off the top of my head, it's a space. So that's just a space. You can go ahead and just put space in all caps just so I know that that's space. All right, next value is 0, 1, 1, 1, 1, 0, 0, 1. All right, so that's going to be 64 and 32 and 16 and 8 plus 1, that's 9. So that's 121. 121 is going to be lowercase y. And for the next number, 0, 0, 1, 1, 0, 1, 1, 1, 1. So that's 64 plus 32 plus 8 plus 4 is 12, 13, 14, 15. So plus 15. Okay, 111, 111. And for 111, we've got a lowercase o. And then for our next value, we've got 0, 1, 1, 1, 0, 1, 0, 1. And that's going to be 64 plus 32 plus 16 plus 5. So that's 117. 117 is going to be a lowercase u. And the next value is going to be 0, 1, 1, 1, 0, 0, 1, 0, 0. 64, 32, 16, and 2 are 18. So that's going to be 114. 114 is going to be a lowercase r. So already we kind of see like maybe our first two words here. What's your? And for the next value, it's 0, 0, 1. So that's our 32 value, which we already know is space. And that looks like we might have one more word here. So the next one is 0, 0, 1, 1, 0, 1, 1, 1. So that's 64 plus 32 plus 8 plus 4 plus 2 is 6. So that's going to be 110. 110 is a lowercase n. I forgot to put the numbers here. Okay, and then this next value is going to be 0, 1, 1, 0, 0, 0, 0, 1. Okay, so that's 64 plus 33, which is 97, which we already know is a, lowercase a. And then our next value is 0, 1, 1, 0, 1, 1, 0, 1. So that's 64 plus 32 plus 13. So that's 109. 109 is lowercase m. You probably already kind of know what the message is by now. Let's go ahead and finish this up. So the next value is 0, 1, 1, 0, 0, 1, 0, 1. So that's 64 plus 32 plus 5, which is 101. Which is a lowercase e. And we've got one more character here for punctuation. And it is 0, 0, and then the rest are 1s. So we know that we could use our little trick. It's going to be 1 less than this guy, so that's going to be 63. If we look at the chart, 63 is going to be down here. It's going to be a question mark. Okay, so now you want to write up the entire message in this text, in the text box below. So it's going to be, what's your name? All right, last part of this assignment is that you're going to answer the question that you decoded up here. What's your name? You're going to include both your text and your binary representation. So if I were to answer this, I could put each character. Some students went ahead and put their last name. You can do that if you would like extra practice, but I'm just going to walk through just my first name. So for my first letter of my first name, that's going to be uppercase S, which is going to be 83. And then I can just go ahead and copy this binary number here. And then for A, we kind of figured that out already, which was 97. And we can go ahead and copy that over. And we can do that for the second A as well. We don't need to look that up separately. And then we also have a lowercase r. So we're going to go over here. It's 114. And the binary number we could just copy in. And that's it.